Okay, let's unpack this. Imagine the most cutting-edge AI technology, the transformer, suddenly revealed to be built upon a foundational mathematical concept from the 1940s.
Yeah, it's pretty wild when you think about it.
Exactly. That's the electrifying realization this paper delivers. It shows that the mysterious attention module in a transformer is, well, at its heart, it's a cubic spline.
A mathematical tool, historically used to draw smooth shapes in engineering, shipbuilding, all sorts of things.
Right. And this isn't just a neat analogy. It means ReLU activated transformers are literally compositions of these well-understood splines. So this deep dive, we're going to unpack this surprising connection. We'll see how understanding this older established math can illuminate the inner workings of our newest AI, offering profound insights into its power and even suggesting better ways to build it. Welcome to the deep dive, where we take a stack of information like this fascinating paper and extract the most important nuggets for you, especially if you're an AI researcher or, an ML engineer looking to stay on top of the latest breakthroughs.
Absolutely.
Today's mission, unraveling the surprising mathematical secret at the core of transformers. We're diving into a paper titled Attention is a Smoothed Cubic Spline by Lai, Lim, and Liu.
And their core claim is pretty bold.
It is that the attention module in a transformer is in fact a smooth cubic spline. This reframes the entire transformer, a cornerstone of modern AI, through the well-established lens of splines, one of applied mathematics' most thoroughly understood tools.
The true aha moment here isn't just a bridge, it's more like a foundational recontextualization. This paper essentially hands us a kind of Rosetta Stone for understanding transformer.
A Rosetta Stone, I like that.
Yeah, showing its inner workings are built on mathematical principles honed over, centuries, really. It offers a fresh lens to understand technologies driving modern AI, like large language models, by connecting them to something truly fundamental.
Right.
The goal, ultimately, is to demystify complex new technology, the transformer, through the robust and, frankly, familiar framework of well-established older mathematics.
So, why does this matter so profoundly for us, the builders and users of AI? Transformers are absolutely everywhere.
Everywhere.
Powering almost every AI breakthrough you hear about, from language processing, which they were originally designed for, to computer vision, robotics, even autonomous vehicles. Their success is phenomenal, truly groundbreaking.
Undeniably.
But the fundamental principles behind them, especially why they work so well, have remained somewhat elusive, right?
Bit of a black box.
Exactly. Many of us have grappled with their black box nature, particularly around the attention module itself, which, ironically, was deemed all you need in the original paper title.
Yeah.
It's the core mechanism that lets transformers weigh the importance of different parts of the input, dynamically shifting focus like a human brain does.
It's the secret sauce.
It is, and this paper goes beyond just observing this phenomenon. It dissects the very mathematical skeleton of components like feed-forward neural networks, attention modules, encoder-decoder blocks, looking at their precise mathematical nature, not just their role in a flowchart.
And if we connect this to the bigger picture, splines are far from new. The word spline itself has this rich, tangible history. Originally, it referred to flexible wooden strips used by shipbuilders, draftsmen.
Oh, wow. Like actual physical things.
Yeah, exactly. Even the Wright brothers notably used them to design the smooth contours of their early aircraft wings. Mathematically, splines have been studied rigorously since the 1940s. They evolved into this mature, profoundly well-understood technology. There was kind of a golden age of approximation theory in the mid to late 20th century focusing on them.
Okay.
Their core purpose is one of our most effective methods for approximating known functions and interpolating unknown ones, basically drawing a smooth curve through a series of points.
You see them everywhere then?
Oh, absolutely. Representing intricate shapes in computer graphics, computer-aided design, even defining the elegant curves of the fonts you're reading right now. They're truly a workhorse of applied mathematics.
It's incredible to think about the ubiquity and richness of history that splines possess. And that, I think, leads directly to a fascinating question. If this foundational math was so well understood, why didn't approximation theorists discover the transformer then? If its core idea was, in some sense, already there.
That's precisely the pivot point of this paper. It comes down to a fundamental difference, both philosophically and practically, in how complicated functions are broken down.
How so?
In classical approximation theory and harmonic analysis, you typically decompose a complex function f into a sum of simpler functions. Think f equals f1 plus f2 plus fr.
Okay, adding things up.
Exactly. This approach is powerful, but it quickly runs into what's known as the curse of dimensionality. As input dimensions grow, the computational effort just explodes.
So if you have a lot of variables, summing up simpler functions becomes exponentially harder.
Precisely. But artificial intelligence, particularly modern deep learning, takes a different path. It decomposes f into a composition of simpler functions, f equal f1, f2 am fr.
Oh, so layering instead of adding.
Right, instead of adding your layering functions, where the output of one becomes the input of the next. This compositional approach is incredibly elegant. It beautifully circumvents the curse of dimensionality and is, in fact, absolutely key to AI success.
Okay.
This is also the underlying mathematical principle behind backpropagation, which is how these layered models are efficiently trained. So while the building blocks might be old, the way they're stacked and combined is an entirely novel and remarkably powerful paradigm.
That's a fascinating distinction, but one might argue. Is this compositional layering truly new? Or are there, historical precedents in math or other fields where sequential operations on simple functions led to complex outcomes? What makes AI's application of it so unique?
That's a great point. Composition of functions is, of course, a fundamental mathematical concept. What's unique in AI, I think, is the scale of these compositions. We're talking tens or hundreds of layers, and the learnable nature of each simple function within that composition.
Okay, so we're not just predefining the layers.
Exactly. We're allowing the network to discover the optimal simple functions through data. And this paper reveals that those discovered functions, particularly the attention modules, happen to be classical splines.
Wow.
And this isn't just an analogy, it's a direct mathematical equivalence. A ReLU activated attention module is not just like a cubic spline, it is a cubic spline.
Can you walk us through that core derivation? How does attention, which we usually think of as this query key value mechanism, mathematically become a cubic spline?
Certainly. So it starts with the understanding that ReLU activated feed-forward neural networks are known to be linear splines.
Okay, piecewise linear. Got it.
Right, think of them as segments of straight lines stitched together. Now, the attention mechanism, specifically the part where you calculate the interaction between queries and keys, often written as a KQ, involves multiplying these linear layers.
Multiplying linear functions. Okay.
When you multiply linear functions, the result is a quadratic function, and therefore a quadratic spline. Then applying the ReLU activation, Max-0, to this quadratic spline still yields a quadratic spline.
It just chops off the negative part.
Precisely. It simply cuts off the negative parts, maintaining its piecewise quadratic nature. Finally, multiplying that result by the value matrix Vx, which is another linear layer, elevates the entire structure into a cubic spline.
Wow. Okay, so linear times linear gives quadratic. ReLU keeps it quadratic. Times linear again gives cubic.
You got it. And this finding applies universally to standard attention, masked attention, encoder-decoder attention. It's fundamental.
So this isn't just a specific type of attention, it's a universal property. And if the attention module itself is a cubic spline, does this necessitate that the entire transformer architecture follows a similar mathematical description? Or could other components maybe diverge from this pattern?
That's the next logical step the paper addresses. If the core building blocks, the attention modules, are cubic splines, and the feed-forward networks are linear splines, then the entire structure, being a composition of these, must also be a composition of splines. And indeed, the paper confirms this. The entire transformer architecture, including encoder blocks, decoder blocks, encoder-decoder blocks, are themselves cubic or higher order splines.
So the whole thing is splines all the way down.
Pretty much. What's more, a T-layer encoder or decoder turns out to be a spline of degree 3T.
3T. Whoa.
Yeah. This elegantly highlights why layering works so effectively to increase model complexity exponentially. Each layer adds a power of 3 to the spline's degree, allowing for incredibly rich and complex function approximation.
Okay, that makes sense. And that brings us to the smoothed part of the title. What does that subtle distinction imply? Why smoothed?
Right. So a traditional mathematical cubic spline is typically C2 continuous.
Okay.
That means it's smooth up to its second derivative, but the third derivative might jump.
Okay, so pretty smooth, but not perfectly smooth everywhere.
Exactly. The original transformer, however, commonly uses Softmax activation in its attention mechanism. This paper clarifies that Softmax acts as a natural way to take that C2 cubic spline and make it a smooth C-infinity function.
C-infinity. Infinitely differentiable.
Infinitely differentiable, yeah. Exceptionally smooth everywhere. This transformation from a potentially, less smooth ReLU activated spline to an infinitely smooth one is precisely where the smooth cubic spline moniker comes from. It's a key detail, indicating how practical AI implementations gain smoothness where the pure mathematical splines might have sharper corners.
Now, for maybe the most profound implication, the one that truly challenges our understanding, can we go the other way? Can any spline, no matter how complex, be represented by a transformer?
Ah, the inverse question.
Yeah. The paper says yes, but it relies on this nearly forgotten mathematical conjecture from 1956. Tell us about the Pierce-Berkhoff Conjecture.
Right, this conjecture, put forth by Richard S. Pierce and Garrett Berkhoff, is foundational here. It states that for every spline, there exists a finite set of polynomials such that the spline can be expressed as a max-min composition of these polynomials.
Max-min composition, okay.
If true, it means splines are max-defineable functions, a class of functions built using maximum and minimum operations on simpler polynomials. Now, this conjecture is known to be true for dimensions 1 and 2.
Which is good, but
for higher dimensions, which are crucial for real-world AI applications, it remains one of mathematics' tantalizing open problems, still unproven after nearly 70 years.
wow. So if this conjecture holds true, it basically means splines are built from these fundamental max-min operations. How does a transformer, with its specific architecture, manage to build any spline? Especially considering it doesn't explicitly have max-min operations everywhere.
That's where the paper's construction proof comes in, and it's really quite brilliant. It lays out the mathematical blueprint, showing how a transformer can systematically construct these splines.
How does it do that?
Well, for instance, the paper shows how even a complex nonlinear building block, like what's known as the Veronese map, which is basically a mathematical lift that transforms data into a higher dimension to find patterns, can be built from just 2 attention modules.
Just 2 attention modules?
Just 2. What's truly remarkable is what these constructions reveal. How every feature of the transformer attention mechanisms, multiple heads, multiple layers, feed-forward networks, plays an essential, non-redundant role in constructing splines.
Non-redundant, so everything is necessary.
Exactly. It's almost as if the inventors of the transformer designed these features not with specific AI applications in mind, but precisely to construct splines as compositions of functions. It's quite an insight.
That's an astonishing claim that the transformer's architecture is, in essence, a spline-building machine.
Indeed. And pulling these threads together, the research suggests this profound equivalence. If the Pierce-Berkhoff conjecture holds true, it means that splines, encoders, max-defineable functions, and linear splines composed with the Veronese map are all essentially different faces of the same mathematical object.
Incredible.
And for those of you specifically interested in language models and sequential data, the paper also extends this. It shows how autoregressive splines, which model sequences where each point depends on previous ones, can be realized as decoders in these transformer architectures.
Ah, so it connects directly to how LLMs generate text.
Directly. It connects the foundational math to the mechanism.
So, okay, beyond the undeniably elegant and surprising math, what's the most compelling practical implication here for our listeners, the people building and deploying these models? What's the immediate takeaway they should apply on Monday morning?
Right, the so what question. Well, the practical implications are pretty significant. First, let's talk about computational efficiency.
Always important.
Definitely. Recent work, like Bortzman and colleagues, shows that ReLU transformers can achieve similar quality to Softmax transformers, but with significant computational savings.
Okay.
Now, if attention is inherently a cubic spline, using ReLU makes it exactly that. It potentially simplifies understanding and optimization without a performance hit.
So for an ML engineer running ReLU transformers,
you're not just getting efficiency, you're leveraging the inherent mathematical purity of a cubic spline. This could open doors to simpler, more direct optimization strategies with proven mathematical backing. You might be able to reason about the network's behavior in ways that were, previously impossible when it felt like a black box.
So it could make our models not just faster, but maybe more interpretable because we have a clearer mathematical handle on them.
Precisely. And this clarity can also lead to better design choices. Which brings me to the second point, smoother activations. If a truly smooth function is desired in your application, maybe for robotics or control systems where continuity is paramount, the paper recommends Soft Plus over Softmax as a more natural, smooth proxy for ReLU.
Soft Plus instead of Softmax. Why?
Well, Soft Plus is mathematically related to ReLU in a very direct way. It's often considered its smooth approximation. Using it preserves fidelity with the underlying spline structure more closely than Softmax does. It could potentially offer superior smoothness and robustness for certain tasks. It's about choosing an activation that aligns with the inherent mathematical properties you're trying to capture.
That's a subtle but potentially powerful distinction for people needing robust, smooth function approximations. Okay, what about the broader long-term impact on research?
This is where it gets really exciting, I think. This connection opens up fascinating new research avenues. The paper points directly back to the Pierce-Berkhoff Conjecture.
Right, the 70-year-old problem.
Exactly. The construction proof explicitly shows that the conjecture is true if and only if every spline is an encoder, meaning it's representable by a transformer encoder.
Wow, so proving the conjecture is equivalent to proving transformers can represent all splines.
That's the connection they make. This deep dive could very well rekindle interest in solving this mathematical problem. Imagine if it's proven true for higher dimensions.
What would that mean?
It wouldn't just be a theoretical triumph. It would provide fundamental guarantees about the representational power of transformers. It could pave the way for entirely new spline-based AI architectures, or even direct algorithms designed from spline theory that parallel or enhance current deep learning methods. It's a powerful testament to the interconnectedness of mathematics and computer science.
It really shows that sometimes the future of AI can be found hiding in a dusty old math textbook.
Absolutely. It's almost poetic, isn't it? A 70-year-old mathematical riddle, maybe gathering dust on a shelf, suddenly becomes a linchpin for understanding the future of AI.
It makes you wonder how many other forgotten mathematical tools are just waiting for the right computational context to explode into relevance.
Precisely. It's a humbling reminder that sometimes the most revolutionary new ideas are simply old truths seen through a different lens. I often find myself thinking, what other obscure theorems might be foundational to the next generation of AI? Perhaps something from knot theory or category theory? Who knows? It definitely encourages a broader, more interdisciplinary approach to AI research. And this raises an important question for you, the listener, to consider. If fundamental AI architectures are essentially sophisticated forms of classical mathematical objects, what other old mathematical tools might hold the key to unlocking the next generation of AI breakthroughs? What ancient concepts are waiting to be reimagined for modern computational problems?
That's a powerful thought, and it really makes you reconsider our current paradigm. What a journey. Connecting ancient shipbuilding techniques to the algorithms powering ChatGPT and other generative AI. This deep dive truly shows that understanding the past can illuminate the future of AI.
Couldn't agree more.
We definitely encourage you to explore the original paper by Lai, Lim, and Liu, and maybe even delve into the fascinating world of splines. Until next time, keep diving deep.